An airbag is a type of vehicle safety device and is an occupant restraint system. The airbag module is designed to inflate extremely rapidly, then quickly deflate during a collision or impact with a surface or a rapid sudden deceleration. It consists of the airbag cushion, a flexible fabric bag, inflation module and impact sensor. The purpose of the airbag is to provide the occupants a soft cushioning and restraint during a crash event to prevent any impact or impact-caused injuries between the flailing occupant and the interior of the vehicle. The airbag provides an energy-absorbing surface between the vehicle's occupant and a steering wheel, instrumental panel, ABC structural body frame pillars, headliner and windshield, windscreen. Description: modern vehicles may contain multiple airbag modules in various configurations including driver airbag module, passenger airbag module, side curtain airbag module, seat-mounted side impact airbag module, knee bolster airbag module, inflatable seat belt modules, front right side airbag sensor, front left side airbag sensor, pedestrian airbag module. During a crash event, the vehicle's crash sensor (S) provide crucial information to the airbag electronic controller unit (AQ), including collision type, angle and severity of impact. Using this information, the airbag electronic controller unit's crash algorithm determines if the crash event meets the criteria for deployment and triggers various firing circuits to deploy one or more airbag modules within the vehicle, working as a supplemental restraint system to the vehicle's seat belt systems. Airbag module deployments are triggered through a pyrotechnic process that is designed to be used once. Newer side impact airbag modules consist of compressed air cylinders that are triggered in the event of a side impact vehicle impact. The first commercial designs were introduced in passenger automobiles during the 1970s with limited success. Broad commercial adoption of airbags occurred in many markets during the late 1980s and early 1990s with a driver airbag and a front passenger airbag as well on some cars. And many modern vehicles now include 6 or more units. Terminology. Over time, various manufacturers have used different terms for airbags. In the 1970s, General Motors marketed its first airbag modules under the unwieldy name of Air Cushion Restraint System, ACRS. Quote, common terms in North America refer to a nominal role as a supplement to active restraints, i.e., seat belts. Because no action by a vehicle occupant is required to activate or use the airbag, it is considered a passive device. This is in contrast to seat belts, which are considered active devices because the vehicle occupant must act to enable them. This terminology is not related to active and passive safety, which are, respectively, systems designed to prevent accidents in the first place, and systems designed to minimize the effects of accidents once they occur. In this usage, a car anti-lock braking system, ABS, will qualify as an active safety device, while both its seat belts and airbags will qualify as passive safety devices. Further terminological confusion can arise from the fact that passive devices and systems, those requiring no input or action by the vehicle occupant, can operate independently in an active manner. An airbag is one such device. Vehicle safety professionals are generally careful in the use of language to avoid this sort of confusion, though advertising principles sometimes prevent such semantic caution in the consumer marketing of safety features, further confusing the terminology. The aviation safety community uses the terms active and passive in the opposite sense from the automotive industry. In patent applications, various airbag manufacturers sometimes use the catch-all term inflatable occupant restraint systems for vehicle airbags. History. Origins. The airbag specified for automobile use traces its origins to air-filled bladders as early as 1941. The invention is also credited independently to the German engineer Walter Linderer, and to the American John W. Hetrick, who in 1951 registered for the first of his airbag patents. Linderer filed German patent number 896,312 on 6 October 1951, which was issued on 12 November 1953. Approximately 3 months after American John Hetrick was issued United States patent number 2,649,311 on 18 August 1953. Linderer's airbag was based on a compressed air system, either released by bumper contact or by the driver. Later research during the 1960s showed that compressed air could not inflate Linderer's airbag fast enough for maximum safety, thus making it an impractical system. Hetrick was an industrial engineer and member of the United States Navy. His airbag was designed based on his experiences with compressed air from torpedoes during his service in the Navy, combined with the desire to provide protection for his family in their automobile during accidents. Hetrick worked with the major American automobile corporations at the time, but they chose not to invest in it. Although airbags are now required in every automobile sold in the United States, Hetrick's 1951 patent filing serves as an example of a valuable invention with little economic value to its inventor because its first commercial use did not occur until after the patent expired, when in 1971, it was installed as an experiment in a few Ford cars. In Japan, Yasuzaburo Kobari started developing an airbag safety net system in 1964, for which he was later awarded patents in 14 countries. He died in 1975 without seeing widespread adoption of airbag systems. In 1967, a breakthrough occurred in the development of airbag crash sensors when Alan K. Breed invented a mechanically based ball-and-tube component for crash detection. An electromechanical sensor with a steel ball attached to a tube by a magnet that would inflate an airbag in under 30 milliseconds. A small explosion of sodium azide instead of compressed air was used for the first time during inflation. Breed Corporation then marketed this innovation first to Chrysler. A similar autoceptor crash restraint, developed by the Eaton, Yale and Town Company for Ford, was soon offered as an automatic safety system in the United States, while the Italian Eaton Livia Company offered a variant with localized air cushions. In the early 1970s, Ford and General Motors began offering cars equipped with airbags. Initially in government fleet-purchased Chevrolet automobiles, GM's Oldsmobile Toronado was the first domestic vehicle to include a passenger airbag. The automaker discontinued the option for its 1977 model year, citing lack of consumer interest. Ford and GM then spent years lobbying against airbag requirements, claiming that the devices were unfeasible and inappropriate. Chrysler made a driver-side airbag standard on 1988 1989 models, but it was not until the early 1990s that airbags became widespread in American cars. As a supplement to seat belts, airbags for passenger cars were introduced in the United States in the mid-1970s, when seat belt usage rates in the country were quite low. Ford built an experimental fleet of cars with airbags in 1971, followed by General Motors in 1973 on Chevrolet vehicles. The early fleet of experimental GM vehicles equipped with airbags experienced 7 fatalities, one of which was later suspected to have been caused by the airbag. In 1974, GM made its Air Cushion Restraint System, ACRS, available as a regular production option, RPO code AR3, in full-size Cadillacs, Buick and Oldsmobile models. The GM cars from the 1970s equipped with ACRS had a driver-side airbag, a driver-side knee restraint, which consists of a padded lower dashboard, and a passenger-side airbag. The passenger-side airbag protects both front passengers and, unlike most newer ones, it integrated a knee cushion and a torso cushion. And it also had dual-stage deployment, which varied depending on the force of the impact. The cars equipped with ACRS had lap belts for all seating positions, but they did not have shoulder belts. Shoulder belts were already mandatory equipment in the United States on closed cars without airbags for the driver and outer front passenger seating positions. But GM chose to market its airbags as a substitute for shoulder belts. The early development of airbags coincided with an international interest in automobile safety legislation. Some safety experts advocated a performance-based occupant protection standard rather than a standard mandating a particular technical solution, which could rapidly become outdated and might not be a cost-effective approach. Nevertheless, as countries successively mandated seatbelt restraints, there was less emphasis placed on other designs for several decades. As a supplemental restraint system, SRS equals frontal airbag equals. The auto industry and research and regulatory communities have moved away from their initial view of the airbag as a seatbelt replacement, and the bags are now nominally designated as supplemental restraint system, SRS, or supplemental inflatable restraints. In 1981, Mercedes-Benz introduced the airbag in West Germany as an option on its flagship saloon model, S-Class, W126. In the Mercedes system, the sensors would automatically pre-tension the seat belts to reduce occupants' motion on impact, now a common feature, and then deploy the airbag on impact. This integrated the seat belts and airbag into a restraint system, rather than the airbag being considered an alternative to the seat belt. In 1987, the Porsche 944 Turbo became the first car to have driver and passenger airbags as standard equipment. The less powerful Porsche 944 and 944S had this as an available option. The same year also saw the first airbag in a Japanese car, the Honda Legend. In 1988, Chrysler was the first United States company to install standard driver's side airbags. They came in 6 lines of its high-volume production passenger cars. The following year, Chrysler became the first United States auto manufacturer to install driver-side airbags in all its domestic-built automobiles. All versions of the Chrysler minivans came with airbags starting January 1991. In 1992, the Jeep Grand Cherokee became the first SUV with airbags in the marketplace. Driver and passenger airbags became standard equipment in all Dodge Intrepid, Eagle Vision, and Chrysler Concorde sedans ahead of any regulations. Early 1993 saw the 4 millionth airbag-equipped Chrysler vehicle roll off the assembly line. In October 1993, the Dodge Rams became the first pickup trucks with airbags. The first known accident between 2 airbag-equipped automobiles took place in 1990 in Virginia, USA. A 1989 Chrysler LeBaron crossed the center line and hit another 1989 Chrysler LeBaron in a head-on collision, causing both driver airbags to deploy. The drivers suffered only minor injuries despite extensive damage to the vehicles. The United States Intermodal Surface Transportation Efficiency Act of 1991 required passenger cars and light trucks built after the 1st of September 1998 to have airbags for the driver and the right front passenger. In the United States, NHTSA estimated that airbags had saved over 4,600 lives by the 1st of September 1999. However, the crash deployment experience of the early 1990s installations indicated that some fatalities and serious injuries were in fact caused by airbags. In 1998, NHTSA initiated new rules for advanced airbags that gave automakers more flexibility in devising effective technological solutions. The revised rules also required improved protection for occupants of different sizes regardless of whether they use seat belts, while minimizing the risk to infants, children, and other occupants caused by airbags. In Europe, airbags were almost entirely absent from mainstream cars until the early 1990s. By 1991, four manufacturers, BMW, Honda, Mercedes-Benz and Volvo, offered the airbag on some of their higher-end models. But shortly afterwards, airbags became a common feature on more mainstream cars. The first European Ford to feature an airbag was the facelifted Escort Mark V in 1992. Within a year, the entire Ford range had at least one airbag as standard. By the mid-1990s, European market leaders such as Vauxhall, Opel, Rover, Peugeot, Renault and Fiat had included airbags as at least optional equipment across their model ranges. By 1999, it was very rare to find a new mass-market car without at least one airbag, and some late 1990s products, such as the Volkswagen Golf MK4, also featured side airbags. The Peugeot 306 is one example of the European automotive mass-market evolution, starting in early 1993. Most of these models did not even offer a driver's airbag as an option. But by 1999, even side airbags were available on several variants. On the other hand, Audi was late to offer airbag systems on a broader scale, since even in the 1994 model year its popular models did not offer airbags. Instead, the German automaker until then relied solely on its proprietary cable-based Pro-Content restraint system. From around the year 2000, side impact airbags became commonplace on even low to mid-range vehicles, such as the smaller-engined versions of the Ford Fiesta and Peugeot 206. And curtain airbags were also becoming regular features on mass-market cars. The Toyota Avensis, launched in 2003, was the first mass-market car to be sold in Europe with 9 airbags. Variable force deployment front airbags were developed to help minimize injury from the airbag itself. Shaped airbags. The Citroën C4 provided the first shaped driver airbag, made possible by this car's unusual fixed hub steering wheel. Side airbag. There are essentially two types of side airbags commonly used today: the side torso airbag and the side curtain airbag. Most vehicles equipped with side curtain airbags also include side torso airbags. However, some, such as the Chevrolet Cobalt 2007-09 model, Chevrolet Silverado, GMC Sierra, and 2009-12 Dodge Ram do not feature the side torso airbag. Side torso airbag. Side impact airbags are side torso airbags. Side thorax, abdomen airbags are a category of airbag usually located in the seater door panel, and inflate between the seat occupant and the door. These airbags are designed to reduce the risk of injury to the pelvic and lower abdomen regions. Most vehicles are now being equipped with different types of designs to help reduce injury and ejection from the vehicle in rollover crashes. More recent side airbag designs include a 2-chamber system, a firmer lower chamber for the pelvic region and softer upper chamber for the rib cage. The Swedish company Autoliv AB was granted a patent on side impact airbags, and they were first offered as an option in 1994 on the 1995 model year Volvo 850. And as standard equipment on all Volvo cars made after 1995. Some cars, such as the 2010 Volkswagen Polo MK5, have combined head and torso side airbags. These are fitted in the backrest of the front seats, and protect the head as well as the torso. Side tubular or curtain airbag. For 1998, the BMW 7 Series and smaller 5 Series were fitted with a tubular-shaped head side airbags. Inflatable tubular structure. It's the head protection system, HPS, as standard equipment. This airbag was designed to offer head protection inside impact collisions and also maintained inflation for up to 7 seconds for rollover protection. However, this tubular-shaped airbag design has been quickly replaced by an inflatable curtain airbag. In May 1998, Toyota began offering a side curtain airbag deploying from the roof on the Prograde. In 1998, the Volvo S80 was given roof-mounted curtain airbags to protect both front and rear passengers. Curtain airbags were then made standard equipment on all new Volvo cars from 2000 except for the first-generation C70, which received an enlarged side torso airbag that also protects the head of front seat occupants. The second-generation C70 convertible received the world's first door-mounted side curtain airbags that deployed upwards. Roll-sensing side curtain airbags found on vehicles more prone to rollovers such as SUVs and pickups will deploy when a rollover is detected instead of just when an actual collision takes place. Often there is a switch to disable the feature in case the driver wants to take the vehicle off-road. Curtain airbags have been said to reduce brain injury or fatalities by up to 45% in a side impact with an SUV. These airbags come in various forms, e.g., tubular, curtain, door-mounted, depending on the needs of the application. Many recent SUVs and MPVs have a long inflatable curtain airbag that protects all 3 rows of seats. Knee airbag equals. The second driver's side and separate knee airbag was used in the Kia Sportage, a Korean SUV launched in 1995, and has been standard equipment since then. The airbag is located beneath the steering wheel. The Toyota Caldina introduced the first driver-side SRS knee airbag on the Japanese market in 2002. Toyota Avensis became the first vehicle sold in Europe equipped with a driver's knee airbag. The Euroncap reported on the 2003 Avensis. There has been much effort to protect the driver's knees and legs, and a knee airbag worked well. Since then, certain models have also included front passenger knee airbags, which deploy near or over the glove compartment in a crash. Knee airbags are designed to reduce leg injury. The knee airbag has become increasingly common from 2000. Rear curtain airbag equals. In 2008, the new Toyota IQ microcar featured the first production rear curtain shield airbag to protect the rear occupants' heads in the event of a rear-end impact. Seat cushion airbag equals. Another feature of the Toyota IQ was a seat cushion airbag in the passenger seat. This is to prevent the pelvis from diving below the lap belt during a frontal impact or submarining. Later Toyota models such as the Yaris added the feature to the driver's seat as well. Center airbag equals. In 2009, Toyota developed the first production rear seat center airbag designed to reduce the severity of secondary injuries to rear passengers in a side collision. This system deploys from the rear center seat, first appearing on the redesigned Crown Majesta. In late 2012, General Motors with supplier Takata introduced a front center airbag. It deploys from the driver's seat. The 2013 GM Traverse, Acadia, and Enclave will be the first vehicles to use a center airbag for center passengers in the front row. Seat belt airbag equals. The seat belt airbag is designed to better distribute the forces experienced by a buckled person in a crash by means of increased seat belt area. This is done to reduce possible injuries to the ribcage or chest of the belt wearer. 2009. Mercedes ESF 2009 experimental safety vehicle had seatbelt airbags. 2010. Lexus LFA had seatbelt airbags for driver and passenger. 2011. Ford Explorer and 2013 Ford Flex. Optional rear seatbelt airbags. Standard on the 2013 Lincoln market. 2013. Mercedes-Benz S-Class W222 has rear seat belt bags. 2014. Ford Mondeo MKV has optional rear seat belt airbags for the two outer seats. Cessna aircraft also introduced seat belt airbags. They are as of 2003 standard on the 172, 182, and 206. Equals pedestrian airbag equals airbag S. Mounted to the exterior of vehicles. So-called pedestrian airbags are designed to reduce injuries in the event of a vehicle-to-pedestrian collision. When a collision is detected, the airbag will deploy and cover hard areas, such as pillars and bonnet edges, before they can be struck by the pedestrian. When introduced in 2012, the Volvo V40 included the world's first pedestrian airbag as standard. As a result, the V40 ranked highest, 88%, in the Euro NCAP's pedestrian tests. The 2014 Land Rover Discovery was fitted with a pedestrian airbag as well. Manufacturers SRS airbag suppliers include Autoliv, Dicel, Takata, TRW and KSS. Formerly Breed, one of the pioneers in the field. On motorcycles, various types of airbags were tested on motorcycles by the UK Transport Research Laboratory in the mid-1970s. In 2006, Honda introduced the first production motorcycle airbag safety system on its Goldwing motorcycle. Honda claims that sensors in the front forks can detect a severe frontal collision and decide when to deploy the airbag, absorbing some of the forward energy of the rider and reducing the velocity at which the rider may be thrown from the motorcycle. Airbag suits have also been developed for use by motorcycle Grand Prix riders. In their earlier form, they were connected to the motorcycle by a cable and deployed when the cable became detached from its mounting clip, inflating to protect the back of the rider. The French manufacturer Helite specializes exclusively in developing airbag jackets for motorcyclists, snowmobile riders and horseback riders. Further developments were conducted by Dainese and led to an autonomous system on board the leathers, without a cable connected to the bike. Instead, an electronic system detects a fall and triggers the inflation of the nitrogen airbags to protect the rider's upper body. Operation. The airbags in the vehicle are controlled by a central airbag control unit, ACU, a specific type of AQ. The ACU monitors a number of related sensors within the vehicle, including accelerometers, impact sensors, side, door, pressure sensors, wheel speed sensors, gyroscopes, brake pressure sensors, and seat occupancy sensors. The bag itself and its inflation mechanism is concealed within the steering wheel boss for the driver, or the dashboard for the front passenger. Behind plastic flaps are doors which are designed to tear open under the force of the bag inflating. Once the requisite threshold has been reached or exceeded, the airbag control unit will trigger the ignition of a gas generator propellant to rapidly inflate a fabric bag. As the vehicle occupant collides with and squeezes the bag, the gas escapes in a controlled manner through small vent holes. The airbag's volume and the size of the vents in the bag are tailored to each vehicle type to spread out the deceleration of, and thus force experienced by, the occupant over time and over the occupant's body. Compared to a seat belt alone, the signals from the various sensors are fed into the airbag control unit, which determines from them the angle of impact, the severity or force of the crash, along with other variables. Depending on the result of these calculations, the ACU may also deploy various additional restraint devices, such as seatbelt pretensioners and/or airbags, including frontal bags for driver and front passenger, along with seat-mounted side bags and curtain airbags which cover the side glass. Each restraint device is typically activated with one or more pyrotechnic devices, commonly called an initiator or electric match. The electric match, which consists of an electrical conductor wrapped in a combustible material, activates with a current pulse between 1 and 3 amperes in less than 2 milliseconds. When the conductor becomes hot enough, it ignites the combustible material, which initiates the gas generator. In a seatbelt pretensioner, this hot gas is used to drive a piston that pulls the slack out of the seatbelt. In an airbag, the initiator is used to ignite solid propellant inside the airbag inflator. The burning propellant generates inert gas which rapidly inflates the airbag in approximately 20 to 30 milliseconds. An airbag must inflate quickly in order to be fully inflated by the time the forward-traveling occupant reaches its outer surface. Typically, the decision to deploy an airbag in a frontal crash is made within 15 to 30 milliseconds after the onset of the crash, and both the driver and passenger airbags are fully inflated within approximately 60 to 80 milliseconds after the first moment of vehicle contact. If an airbag deploys too late or too slowly, the risk of occupant injury from contact with the inflating airbag may increase, since more distance typically exists between the passenger and the instrument panel. The passenger airbag is larger and requires more gas to fill it. Older airbag systems contained a mixture of sodium azide, sodium nitride, KNO3, and silicon oxide. A typical driver side airbag contains approximately 50 to 80 grams of sodium nitride, with the larger passenger side airbag containing about 250 grams, within about 40 milliseconds of impact. All these components react in 3 separate reactions that produce nitrogen gas. The reactions, in order, are as follows. 1. 2 sodium nitride 2 Na plus 3 N2. G. 2. 10 Na plus 2 KNO3 K2O plus 5 sodium oxide plus N2. G. 3. K2O plus sodium oxide plus 2 silicon oxide K2 silicon oxide plus sodium metasilicate. Silicate glass. The first reaction is the decomposition of sodium nitride under high temperature conditions using an electric impulse. This impulse generates to 300 degrees Celsius temperatures required for the decomposition of the sodium nitride, which produces Na metal and N2 gas. Since Na metal is highly reactive, the KNO3 and silicon oxide react and remove it, in turn producing more N2 gas. The second reaction shows just that. The reason that KNO3 is used rather than something like sodium nitrate is because it is less hygroscopic. It is very important that the materials used in this reaction are not hygroscopic because absorbed moisture can desensitize the system and cause the reaction to fail. The final reaction is used to eliminate the K2O and sodium oxide produced in the previous reactions. Because the first period metal oxides are highly reactive, these products react with silicon oxide to produce a silicate glass, which is a harmless and stable compound. According to her patent, the particle size of the sodium azide, potassium nitrate, and silicon dioxide are important. The sodium nitride in KNO3 must be between 10 and 20 micrometers, while the silicon oxide must be between 5 and 10 micrometers. There are ongoing efforts to find alternative compounds that can be used in airbags which have less toxic byproducts. In a journal article by Akayoshi al., it was found that for the reaction of the senior complex nitrate, senior, NH2NHCONHNH2, NO3, 2 of carbohydrazide, SRCDH, with various oxidizing agents resulted in the evolution of N2 and CO2 gases. Using potassium hypobromite as the oxidizing agent resulted in the most vigorous reaction as well as the lowest initial temperature of reaction. The N2 and CO2 gases evolved made up 99% of all gases evolved. Nearly all the starting materials won't decompose until reaching temperatures of 500 degrees Celsius or higher, so this could be a viable option as an airbag gas generator. In a patent containing another plausible alternative to sodium nitride-driven airbags, the gas-generating materials involved the use of guanidine nitrate, 5-aminotetrazole, bitetrazole dihydrate, nitroimidazole, and basic copper nitrate. It was found that these non-azide reagents allowed for a less toxic, lower combustion temperature reaction and more easily disposable airbag inflation system. Front airbags normally do not protect the occupants during side, rear, or rollover accidents. Since airbags deploy only once and deflate quickly after the initial impact, they will not be beneficial during a subsequent collision. Safety belts help reduce the risk of injury in many types of crashes. They help to properly position occupants to maximize the airbag's benefits, and they help restrain occupants during the initial and any following collisions. In vehicles equipped with a rollover sensing system, accelerometers and gyroscopes are used to sense the onset of a rollover event. If a rollover event is determined to be imminent, side curtain airbags are deployed to help protect the occupant from contact with the side of the vehicle interior, and also to help prevent occupant ejection as the vehicle rolls over. Triggering conditions. Airbags are designed to deploy in frontal and near-frontal collisions more severe than a threshold, defined by the regulations governing vehicle construction in whatever particular market the vehicle is intended for. United States regulations require deployment in crashes at least equivalent in deceleration to a 23 km per hour, 14 miles per hour, barrier collision, or similarly, striking a parked car of similar size across the full front of each vehicle at about twice the speed. International regulations are performance-based, rather than technology-based, so airbag deployment threshold is a function of overall vehicle design. Unlike crash tests into barriers, real-world crashes typically occur at angles other than directly into the front of the vehicle, and the crash forces usually are not evenly distributed across the front of the vehicle. Consequently, the relative speed between the striking and struck vehicle required to deploy the airbag in a real-world crash can be much higher than an equivalent barrier crash, because airbag sensors measure deceleration. Vehicle speed is not a good indicator of whether an airbag should have deployed. Airbags can deploy due to the vehicle's undercarriage striking a low object protruding above the roadway due to the resulting deceleration. The airbag sensor is a MEMS accelerometer, which is a small integrated circuit with integrated micromechanical elements. The microscopic mechanical element moves in response to rapid deceleration, and this motion causes a change in capacitance, which is detected by the electronics on the chip that then sends a signal to fire the airbag. The most common MEMS accelerometer in use is the ADXL50 by analog devices, but there are other MEMS manufacturers as well. Initial attempts using mercury switches did not work well. Before MEMS, the primary system used to deploy airbags was called a rollermite. A rollermite is a mechanical device consisting of a roller suspended within a tensioned band. As a result of the particular geometry and material properties used, the roller is free to translate with little friction or hysteresis. This device was developed at Sandia National Laboratories. The rollermite and similar macro-mechanical devices were used in airbags until the mid-1990s when they were universally replaced with MEMS. Nearly all airbags are designed to automatically deploy in the event of a vehicle fire when temperatures reach 150 to 200 degrees Celsius, 300 to 400 degrees Fahrenheit. This safety feature, often termed auto-ignition, helps to ensure that such temperatures do not cause an explosion of the entire airbag module. Today, airbag triggering algorithms are becoming much more complex. They try to reduce unnecessary deployments and to adapt the deployment speed to the crash conditions. The algorithms are considered valuable intellectual property. Experimental algorithms may take into account such factors as the weight of the occupant, the seat location, seatbelt use, and even attempt to determine if a baby seat is present. Inflation equals. When the frontal airbags are to deploy, a signal is sent to the inflator unit within the airbag control unit. An igniter starts a rapid chemical reaction generating primarily nitrogen gas, N2, to fill the airbag, making it deploy through the module cover. Some airbag technologies use compressed nitrogen or argon gas with a pyrotechnic-operated valve hybrid gas generator, while other technologies use various energetic propellants. Although propellants containing the highly toxic sodium azide, sodium nitride, were common in early inflator designs, little to no toxic sodium azide has been found on used airbags. The azide-containing pyrotechnic gas generators contain a substantial amount of the propellant. The driver side airbag would contain a canister containing about 50 grams of sodium azide. The passenger side container holds about 200 grams of sodium azide. The alternative propellants may incorporate, for example, a combination of nitroguanidine, phase-stabilized ammonium nitrate, NH4NO3, or other non-metallic oxidizer, and a nitrogen-rich fuel different from azide, e.g., tetrazoles, triazoles, and their salts. The burn rate modifiers in the mixture may be an alkaline metal nitrate, NO3, or nitrite, NO2, dicyanamide or its salts, sodium borohydride, NiBH4, etc. The coolants and slag formers may be e.g., clay, silica, alumina, glass, etc. Other alternatives are e.g., nitrocellulose-based propellants, which have high gas yield but bad storage stability, and their oxygen balance requires secondary oxidation of the reaction products to avoid buildup of carbon monoxide, or high-oxygen nitrogen-free organic compounds within organic oxidizers, e.g., diatricarboxylic acids with chlorates, chlorine trioxide, or perchlorates, chlorine tetroxide, and eventually metallic oxides. The nitrogen-free formulation avoids formation of toxic nitrogen oxides. From the onset of the crash, the entire deployment and inflation process is about 0.04 seconds. Because vehicles change speed so quickly in a crash, airbags must inflate rapidly to reduce the risk of the occupant hitting the vehicle's interior. Variable force deployment. Advanced airbag technologies are being developed to tailor airbag deployment to the severity of the crash, the size and posture of the vehicle occupant, belt usage, and how close that person is to the actual airbag. Many of these systems use multi-stage inflators that deploy less forcefully in stages in moderate crashes than in very severe crashes. Occupant sensing devices let the airbag control unit know if someone is occupying a seat adjacent to an airbag, the mass, weight of the person, whether a seat belt or child restraint is being used, and whether the person is forward in the seat and close to the airbag. Based on this information and crash severity information, the airbag is deployed at either at a high force level a less forceful level, or not at all. Adaptive airbag systems may utilize multi-stage airbags to adjust the pressure within the airbag. The greater the pressure within the airbag, the more force the airbag will exert on the occupants as they come in contact with it. These adjustments allow the system to deploy the airbag with a moderate force for most collisions, reserving the maximum force airbag only for the severest of collisions. Additional sensors to determine the location, weight or relative size of the occupants may also be used. Information regarding the occupants and the severity of the crash are used by the airbag control unit to determine whether airbags should be suppressed or deployed, and if so, at various output levels. Post-deployment equals. A chemical reaction produces a burst of nitrogen to inflate the bag. Once an airbag deploys, deflation begins immediately as the gas escapes through vent S in the fabric, or, as it's sometimes called, the cushion, and cools. Deployment is frequently accompanied by the release of dust-like particles and gases in the vehicle's interior, called effluent. Most of this dust consists of cornstarch, French chalk, or talcum powder, which are used to lubricate the airbag during deployment. Newer designs produce effluent primarily consisting of harmless talcum powder, cornstarch and nitrogen gas. In older designs using an azide-based propellant, usually sodium nitride, varying amounts of sodium hydroxide nearly always are initially present. In small amounts this chemical can cause minor irritation to the eyes and/or open wounds. However, with exposure to air, it quickly turns into sodium bicarbonate, baking soda. However, this transformation is not 100% complete, and invariably leaves residual amounts of hydroxide ion from NaOH. Depending on the type of airbag system, potassium chloride may also be present. For most people, the only effect that dust may produce is some minor irritation of the throat and eyes. Generally, minor irritations only occur when the occupant remains in the vehicle for many minutes with the windows closed and no ventilation. However, some people with asthma may develop a potentially lethal asthmatic attack from inhaling the dust, because of the airbag exit flap design of the steering wheel boss and dashboard panel. These items are not designed to be recoverable if an airbag deploys, meaning that they have to be replaced if the vehicle has not been written off in an accident. Moreover, the dust-like particles and gases can cause irreparable cosmetic damage to the dashboard and upholstery, meaning that minor collisions which result in the deployment of airbags can be costly accidents, even if there are no injuries and there is only minor damage to the vehicle structure. Regulatory specifications. United States. On the 11th of July 1984, the United States government amended Federal Motor Vehicle Safety Standard 208, FMVSS 208, to require cars produced after the 1st of April 1989 to be equipped with a passive restraint for the driver. An airbag or a seat belt would meet the requirements of the standard. Airbag introduction was stimulated by the National Highway Traffic Safety Administration. However, airbags were not mandatory on light trucks until 1997. In 1998, FMVSS 208 was amended to require dual front airbags and reduced power. Second-generation airbags were also mandated. This was due to the injuries caused by first-generation airbags. Though FMVSS 208 continues to require that bags be engineered and calibrated to be able to save the life of an unbelted 50th percentile size and weight male crash test dummy. Technical performance and validation requirements for the inflator assembly used in airbag modules are specified in SAE USCAR 24-2. Outside the United States, some countries outside North America adhere to internationalized European ECE vehicle and equipment regulations rather than the United States Federal Motor Vehicle Safety Standards. ECE airbags are generally smaller and inflate less forcefully than United States airbags. Because the ECE specifications are based on belted crash test dummies. In the United Kingdom, and most other developed countries, there is no direct legal requirement for new cars to feature airbags. Instead, the Euro NCAP vehicle safety rating encourages manufacturers to take a comprehensive approach to occupant safety. A good rating can only be achieved by combining airbags with other safety features. Thus, almost all new cars now come with at least 2 airbags as standard. Maintenance. Inadvertent airbag deployment while the vehicle is being serviced can result in severe injury, and an improperly installed defective airbag unit may not operate or perform as intended. Some countries impose restrictions on the sale, transport, handling, and service of airbags and system components. In Germany, airbags are regulated as harmful explosives. Only mechanics with special training are allowed to service airbag systems. Some automakers, such as Mercedes-Benz, call for the replacement of undeployed airbags after a certain period of time to ensure their reliability in an accident. One example is the 1992 S500, which has an expiry date sticker attached to the door pillar. Some Skoda vehicles indicate an expiry date of 14 years from the date of manufacture. In this case, replacement would be uneconomic as the car would have negligible value at 14 years old, far less than the cost of fitting new airbags. Volvo, on the other hand, has stated airbags do not require replacement during the lifetime of the vehicle, though this cannot be taken as a guarantee on the device. Limitations. Although the millions of installed airbags in use have an excellent safety record, there are some limitations on their ability to protect car occupants. The original implementation of front airbags did little to protect against side collisions, which can be more dangerous than frontal collisions because the protective crumple zone in front of the passenger compartment is completely bypassed. Side airbags and protective airbag curtains are increasingly being required in modern vehicles to protect against this very common category of collisions. Airbags are designed to deploy once only, and are ineffective if there are any further collisions after an initial impact. Multiple impacts may occur during certain rollover accidents or other incidents involving multiple collisions, such as many multi-vehicle collisions. An extremely dangerous situation occurs during underride collisions, in which a passenger vehicle collides with the rear of a tractor-trailer lacking a rear underride guard, or hits the side of such a trailer not equipped with a side underride guard. The platform bed of a typical trailer is approximately at the head height of a seated adult occupant of a typical passenger car. This means that there may not be much between a head and the edge of the trailer platform, except a glass windshield. In an underride collision, the car's crush zones designed to absorb collision energy are completely bypassed, and the airbags may not deploy in time because the car does not decelerate appreciably until the windshield and roof pillars have already impacted the trailer bed. Even delayed inflation of airbags may be useless because of major intrusion into the passenger space, leaving occupants at high risk of major head trauma or decapitation in even low-speed collisions. Western European standards for underride guards have been stricter than North American standards, which typically have allowed grandfathering of older equipment that may still be on the road for decades. Typical airbag systems are completely disabled by turning off the ignition key. Unexpected turn-offs usually also disable the engine, power steering, and power brakes, and may be the direct cause of an accident. If a violent collision occurs, the disabled airbags will not deploy to protect vehicle occupants. In 2014, General Motors admitted to concealing information about fatal accidents caused by defective ignition switches which would abruptly shut down a car, including its airbags. Between 13 and 74 deaths have been directly attributed to this defect, depending on how the fatalities are classified. Injuries and fatalities. Under some rare conditions, airbags can injure and in some very rare instances kill vehicle occupants. To provide crash protection for occupants not wearing seat belts, United States airbag designs trigger much more forcefully than airbags designed to the international ECE standards used in most other countries. Recent, smart airbag controllers can recognize if a seatbelt is used, and alter the airbag cushion deployment parameters accordingly. In 1990, the first automotive fatality attributed to an airbag was reported. TRW produced the first gas-inflated airbag in 1994, with sensors and low inflation force bags becoming common soon afterwards. Dual depth, also known as dual stage, airbags appeared on passenger cars in 1998. By 2005, deaths related to airbags had declined, with no adult deaths and 2 child deaths attributed to airbags that year. However, injuries remain fairly common in accidents with an airbag deployment. Serious injuries are less common, but severe or fatal injuries can occur to vehicle occupants very near an airbag or in direct contact when it deploys. Such injuries may be sustained by unconscious drivers slumped over the steering wheel, unrestrained or improperly restrained occupants who slide forward in the seat during pre-crash braking, and properly belted drivers sitting very close to the steering wheel. A good reason for the driver not to cross hands over the steering wheel. A rule taught to most learner drivers but quickly forgotten by most, is that an airbag deployment while negotiating a turn may result in the driver's hand being driven forcefully into his or her face, exacerbating any injuries from the airbag alone. Improvements in sensing and gas generator technology have allowed the development of third-generation airbag systems that can adjust their deployment parameters to size, weight, position and restraint status of the occupant. These improvements have demonstrated a reduced injury risk factor for small adults and children, who had an increased risk of injury with first-generation airbag systems. One model of airbags made by the Takata Corporation used ammonium nitrate-based gas-generating compositions in airbag inflators instead of the more stable, but more expensive compound tetrazole. The ammonium nitrate-based inflators had a flaw where old inflators with long-term exposure to hot and humid climate conditions could rupture during deployment, projecting metal shards through the airbag and into the driver. The defect caused 7 deaths and over 100 injuries in the U.S., and 1 death in Malaysia. The National Highway Traffic Safety Administration recalled over 33 million vehicles in May 2015, and fined Takata $70 million in November 2015. Toyota, Mazda and Honda have said that they will not use ammonium nitrate inflators. Airbag fatality statistics. From 1990 to 2000, the United States National Highway Traffic Safety Administration identified 175 fatalities caused by airbags. Most of these, 104, have been children, while the rest were adults. About 3.3 million airbag deployments have occurred during that interval, and the agency estimates more than 6,377 lives saved and countless injuries prevented. A rear-facing infant restraint put in the front seat of a vehicle places an infant's head close to the airbag, which can cause severe head injuries or death if the airbag deploys. Some modern cars include a switch to disable the front passenger airbag, in case a child supporting seat is used there. Although not in Australia, where rear-facing child seats are prohibited in the front where an airbag is fitted. In vehicles with side airbags, it is dangerous for occupants to lean against the windows, doors, and pillars, or to place objects between themselves and the side of the vehicle. Articles hung from a vehicle's clothes hanger hooks can be hazardous if the vehicle's side curtain airbags deploy. A seat-mounted airbag may also cause internal injury if the occupant leans against the door. Aerospace and military applications. The aerospace industry and the United States government have applied airbag technologies for many years. NASA and United States Department of Defense have incorporated airbag systems in various aircraft and spacecraft applications as early as the 1960s. Airbag landing systems. The first use of airbags for landing were Luna 9 and Luna 13, which landed on the Moon in 1966 and returned panoramic images. The Mars Pathfinder lander employed an innovative airbag landing system, supplemented with aerobraking, parachute, and solid rocket landing thrusters. This prototype successfully tested the concept, and the two Mars exploration rover mission landers employed similar landing systems. The Beagle 2 Mars lander also tried to use airbags for landing. The landing was successful and the lander touched down safely, but several of the spacecraft's solar panels failed to deploy, thereby disabling the spacecraft. Airbags have also been used on military fixed-wing aircraft, such as the escape crew capsule of the F-111 Aardvark. Occupant protection. The United States Army has incorporated airbags in its UH-60A Polita Black Hawk and OH-58D Kiowa Warrior helicopter fleets. The cockpit airbag system, CABS, consists of forward and lateral airbags, and an inflatable tubular structure, on the OH-58D only, with an electronic crash sensor unit, ECSU. The CABS system was developed by the United States Army Aviation Applied Technology Directorate, Fort Eustis, VA through a contract with Similar Safety Systems, now BAE Systems. It is the first conventional airbag system for occupant injury prevention worldwide, designed and developed and placed in service for an aircraft, and the first specifically for helicopter applications. See also: airbag dermatitis, airplane airbags, automobile safety, pre-crash system, safety standards, chemistry behind airbags, pictures and details about the 1970s GM air cushion restraint system. The promise of the airbag looks at a history of airbags and how the technology gave rise to today's smart cars. Quote,